So we were studying inter-domain routing protocol, BGP. Let me first see how much you remember. Let me flash this figure to jog your memory. Basically, BGP has eBGP sessions and iBGP sessions. The eBGP sessions are used to exchange IP prefix information, and the routing algorithm that is followed there is the path vector algorithm. An important point to note is that an AS need not export all the IP prefixes it has learned. We will see this as part of exporting routes, and similarly, whatever routes it has heard about, it may not import them. This is covered under importing routes. So via eBGP, whatever routes you have learned, you install in the routers within the AS via the iBGP sessions. Both the IGP protocol as well as the EGP protocol, that is the border gateway protocol, together work to fill the forwarding table at a router. So with this background, let's first look at exporting routes. So let's look at this ISP. This ISP has some internal IP prefixes, by which I mean the customers that this ISP is serving. It knows how to reach all these internal IP prefixes via its internal routers. Not only that, this ISP may have heard of IP prefix 1, by which I mean this is not just one single IP prefix but a set of IP prefixes, and similarly it would have heard a bunch of IP prefix from some other border gateway router. So these I am representing in this. So it has a whole bunch of IP prefixes. Now out of these, it has to decide which IP prefixes to advertise to the other ISPs. So what does a router advertisement mean? Let's get this straight. For example, let's say this is a border gateway router B, which is connected to another border gateway router A that belongs to another ISP. Now if B were to advertise a given IP prefix, say P, it is basically telling A that if you send me a packet with the destination as P, I will deliver that packet to the intended destination. So that is the service B is providing to A. If you don't want to provide certain service, you should ensure that you do not advertise the prefixes to this router A. So this will become clear as we proceed further. This ISP has many customers, and the IP prefixes for this customers, let me call them IPF. So this IPF, should it expose to an ISP that is providing service to it? And should it expose it to a peer that is providing peering service to it? What do you think? Well, the customer routes, it should ideally expose to everyone because you are taking money from the customers to provide this service. And as more and more traffic goes to the customers will need fatter and fatter pipes, thereby you will make more revenue. So the customer routes you have to expose to whatever peering relation or the transit relation that you have. Now suppose this ISP learned about certain IP prefixes, let me call them again IPF, from its provider. Now these IP prefixes, do you think it should expose to the peer? That is another ISP with which it has a peering relation? Definitely not. If you were to export it, what the peer will do is to reach some network within this, it will now start sending data via you. These networks that are represented by these IP prefixes are not your customers. So in which case you are carrying traffic from the peer ISP to the provider ISP where you are not getting any benefit out of it. So you should not export these prefixes you have learned from your provider to your peer. Now what about, should you expose them to your customers? Yes, you should expose them to the customers because you are providing the service to your customers. So the customer should know how to reach this other information. So they will go via you. That is why they are paying you the money for it. So the transit provider routes are exported to the customers but not to the peers. What about peer routes? Again, this ISP is going to hear certain IP prefixes from the peers. Now these information, should it expose to the provider ISP? Well, again no, because if you were to expose it to the provider may now start using you to deliver traffic to the particular peer. And again, this traffic has no relevance to you, so you should not export the peer prefixes to your provider. What about exposing them to your customers? Again, the same logic, your customers, you are providing a service, and peering is mainly established for not going via the provider. So if you expose it, the customer traffic can now go in this particular direction. What about exposing the information you heard from one peer to the other peer that you are connected with? Again, no, because then this peer will use you to send traffic to this other peer, and again you are not going to get much out of this particular traffic. So basically, in this particular case, you export this prefixes that you have learned from the peer to the customers, but not to other peers or the provider. So this is how you control what traffic flows within your autonomous system. Basically, what this all boils down to is also that you only want your customer traffic to go through your ISP. You don't want any other extraneous traffic to go through you. So the earlier slides were telling what routes to export. Now in this process, you are going to hear about many routes. Now you have to decide what routes to import. A router within an ISP is going to hear about routes, and these routes can come from different sources. So this route to a given destination can come from a customer, or it can come from a peer, or it can come from a provider. Now which route should it install? So the policy there is this, that the customer route should be given more preference over peer and provider. Why like this? Suppose a customer said, you can reach me via this particular IP prefix. A customer router is saying this, and the peer also is also telling this, maybe because this customer is multi-homed. And since you're directly connected, you want better performance for the customers. So you should import the route provided by the customer over the route provided by the peer. And now why peer over provider? Because I mentioned this reason earlier. If peer is providing a route, this money, there is no money involved here. So if you send, you are not going to have to pay any money. But if you send it via the provider, then you have to pay the money to the provider. In other words, if the peer has a route to the same destination and the provider also has a route to the same destination, you would prefer peer over the provider. As you can see, very complex policies, what IP prefixes to export, what IP prefixes to import, all of this is a function of the kind of relationship you have with your other ISPs. Based on the above rules, an autonomous system may know about a lot of IP prefixes. This is a big set, and when it is exporting, it may export only a subset of these IP prefixes. And let's look at one specific IP prefix that it has exported. The same logic will apply to other IP prefixes as well. So when it export this particular IP prefix, it is basically telling that this particular prefix I can provide a path to. That is what it is telling. Now once this AS2 receives this particular IP prefix, then again it will apply its own rule, and let's again say it also decided to export this. So it is now going to tell AS3 that I can provide a path to this particular IP prefix P. Now the routing that is employed as part of this advertisement process is path vector routing, which we briefly mentioned when we covered distance vector. So basically AS2 will advertise I can reach P via AS1, AS2. Similarly, AS4, when it receives this advertisement, it will note that I can reach P via AS1, AS4, and it is going to advertise this. Now suppose AS2 decided that it wants to reach prefix P via this path, and when it were to advertise this, the vector that it is going to generate is P I am going to reach via this. And this vector, it is going to advertise it to its neighbors. Let's say it came to AS1 as well as AS3. Now AS1, since it sees itself within this, it is not going to act on this particular information because it's there as part of the path. So this is how you avoid looping as part of this routing process. So to facilitate this kind of path vector routing, each autonomous system is assigned a unique number, which is a 16-bit number by a central authority. The fact that we are using path vector, it prevents routing, and this path vector can also permit policy-based routing. For example, if AS1 saw two paths, one let's say via AS2, AS3 to some destination D and another via AS2, AS4, AS5 to the same destination D, and if AS3 were its competitor and it doesn't want to send, even though this is kind of relatively short, you don't really know because you don't know how many internal routers it is passing through, it will not select this path, it will select this path. Now let's all put it together, integrating this intra and inter-domain routing. So again here I have shown a particular autonomous system which has border gateway routers A, C and F, and based on this BGP sessions, this border gateway routers have heard about prefixes and they also found out what is the path to take to reach these prefixes. For example, it may have heard about this prefix from multiple border gateway routers, but based on, let's say, whatever policy it has, it will, let's say it has decided this over this. So that and all, it figures out internally what to do about that. Now, whatever information they have figured out, what they do is they established iBGP sessions to each of these routers and convey this information. By the way, the iBGP session between A and D, while I represent like this is a logical view, whereas internally when it goes from here to here, it actually passes over the router P. But since I said it is a TCP connection, this iBGP sessions, internally the routing between A and D is handled by the interior gateway protocol. We don't have to worry about it. Now, based on this iBGP sessions, all the routers within this particular autonomous system have this BGP table for the autonomous system. So they know that to reach this, you have to go via A, to go reach this, you have to again go via A, to reach this, you have to go via C, and to reach this, you have to go via F. So this information is consistent across all the routers, and this consistency was achieved by the iBGP sessions. Now let's look at this specific router B. This specific router has an interior gateway table. This must have been gotten either through RIP or OSPF, and this is saying how to reach the different routers. What is the next hop to take? Combining these both is where you arrive at the forwarding table at router B. You know that to reach this particular IP prefix, you have to send it to this border gateway router, and to reach this border gateway router, you need to go through this. So you go in here. So here again, it's the same. Let's look at this specific case. So 10.0.0.8, the next BGP hop is this, but to reach this C, your internal gateway is saying you have to go through D, thereby to reach this prefix you send it to D. So this is how you integrate intra and inter-domain routing. So why do we have inter and intra-domain routing? For various reasons. One is policy, where ISPs want control over how their traffic is routed, and if you want policy, you need to go for inter-domain routing. But within an autonomous system, there is no policy decisions because everything is being controlled by a single administration. There you can focus on performance. So that is what this is saying. As far as inter-domain is concerned, policy dominates performance, whereas intra-domain is concerned, one can focus on performance. And scale is again handled via imposing an additional hierarchy via separating out inter and intra-domain routing. For example, if you're doing link state routing as part of the intra-domain routing, you're not really flooding your packets across autonomous systems. It is contained within your own autonomous system, so it scales well. These border gateway routers will summarize that information and pump it into the other autonomous systems via the inter-domain routing. Now the complexity of the exterior gateway protocol, that is employing path vector, is roughly of the order of the number of autonomous systems. There will only be a few border gateway routers per autonomous systems, and the number of autonomous systems themselves are not going to be that many. So this complexity is also easily handled. And when you look at the interior gateway protocol, the complexities will be roughly of the order of the number of networks within the single autonomous systems. Because often a router has to interconnect one or two of these networks. So by splitting the routing into inter and intra, one could handle policy, performance to some extent, and scale. So to summarize, the internet architecture is very complex with different relations between the ISPs, and this tends to complicate routing. We saw that this complexity can be handled via inter and intra-domain routing, where policy dominates the inter-domain routing. The protocol that facilitates inter-domain routing is the BGP protocol. This is common across all the autonomous systems, and this is managed via eBGP and iBGP sessions. How you export, how you import rules, all these are based on the relationship between the ISPs, and we also saw how the intra and inter-domain routing work together to build forwarding tables. A big round of applause. We have finished network layer.